Okay, when left off, we were in part one, we were mentioning surface tension and how the water molecules or any polar covalent compound, they pull together towards each other, and that's why we have surface tension. So I pulled this diagram off the internet. This is a picture of a droplet of, it can be any polar covalent compound, but let's just call it water. And each one of these balls represents a water molecule, and they're pulled towards each other. Do you see the little arrows where they're all pulled towards each other? And when they pull towards each other, but not really pull towards the air, that's what forms the droplet. And the size of the droplet, or how the droplet bubbles up, I don't know quite how to say that. The give up, I give up. How much the droplet bubbles up or beads up, the size of the beading will indicate information about the strength of the intermolecular forces. For example, if it beads up really tall and high, that's like water does that, because the water molecules are very strongly attracted to each other. Not as much as ionic compounds, but in terms of covalent compounds, water is a fairly strongly attracted covalent compound. But if we did something that has a smaller attraction, our bead of our liquid won't be quite as tall. So, for example, we're going to do in class, I can't wait to do it, we're going to do hexane in class. I'm going to give something away. Here's the table. The hexane droplet's going to be like this. It's going to barely bead up. And it's going to barely bead up because the hexane has a very weak attraction for itself. It's going to have weak intermolecular forces. And we're going to talk about why hexane has weaker intermolecular forces than water right now, because we're going to move along and talk about our last kind of compound. Our last kind of compound is a nonpolar covalent compound. So in a nonpolar covalent compound, we are still sharing electrons, but we have an even or equal distribution of charge. No one element is going to pull electrons towards another end more than another. So I'm going to look at methane. Methane is CH4. And I'm going to intentionally not draw these looking in 3 dimensions. I'm going to draw these just in 2 dimensions. It makes the diagram easier to look at. And so this is methane, CH4, methane. Write that down so you'll know it, CH4. It's the main component of natural gas. When we talk about natural gas, methane is the main component. I want to remind you that this bond between carbon and hydrogen is pretty strong. We are not breaking these right now. These are not broken in physical changes. We are not discussing what's happening to these guys right now. Same as we did as above, as before. We are discussing what happens between the molecules. That's what we're focusing on. We're focusing on intermolecular forces. We are focused on what happens between the molecules, the IMF, or the intermolecular force. In a nonpolar covalent compound, these are very, very weak. And being that those have very, very, very weak intermolecular forces, that causes nonpolar covalent compounds to have particular properties. One property that they tend to have is very low melting points. It's very easy to melt them because that attraction is very weak. Very low melting points. I'm going to put in parentheses, weak attraction. And after attraction, I'm going to put IMF, intermolecular force. They are not strongly attracted to each other, so they melt very easily. They have little, let me not say little. They have very low surface tension. So look back above or look back before where I talked about how the hexane doesn't bubble up very much. They have a very low surface tension. Oops, that's supposed to be the word tension. And they tend to be volatile, which means evaporates easily. And often they are a gas at room temperature for this reason. A gas at room temperature for this reason, because they evaporate easily. So, for example, the hexane, we've used it before. The hexane was the one I poured down the ramp, down to the candle, and it caught on fire, and it was really cool, and everybody loved it. Well, the hexane evaporates very easily. It is very volatile because it has these weak intermolecular forces between it. Now, because this is a covalent compound, it will still not conduct electricity in any circumstance. Or when I say any circumstance, I mean in regular high school chemistry. These guys will not conduct electricity. Okay, let's finish today with the three types of intermolecular forces. Three types of intermolecular forces. I'm going to call this IMF. This is very important. IMF, there are three kinds. There is hydrogen bonding, which remember is not really bonding at all, but just an attraction. I'm going to put attraction in parentheses. I wish whoever came up with it, and I don't know that off the top of my head, I wish the person who came up with it had called it hydrogen attraction. Would have made my life much easier. There are dipole-dipole forces, or dipole-dipole attraction. You can say whatever you want. And there are London, after Fritz London, I think was his name, dispersion forces. Hydrogen bonding happens in polar molecules. So first off, you have to be covalent. Obviously, this is all for covalent. Ionic compounds are in their own little world. You have to be covalent, you have to be polar, and it has to have N, O, or F as the central atom. And obviously it has to have hydrogen in it. And so when we run into a situation where we have NOF, a central atom, and hydrogen, we know that those molecules are attracted via hydrogen bonding. Hydrogen bonding is how they're attracted. It is the strongest of the three types of bonds if we're comparing the same size molecule. And I'll tell you what I mean by that in just a minute, okay? So it is considered the strongest of the three types of intermolecular forces. Water is an excellent example of a compound that is considered to undergo hydrogen bonding, and here's what happens. We have this very negative end over here, and we have this very positive hydrogen. What happens is, which is positive over here, what happens is that hydrogen can get super close to those electrons, and the fact that they can get super close makes them bonded pretty strongly in terms of intermolecular forces, that is. Okay, and that's why water has very many special properties, and we'll talk about some of those as we go on. Let's go to our next type of intermolecular force, dipole-dipole attraction, or dipole-dipole forces. First off, I want you to notice that the word di, the prefix di, means two, pole means polar, and so this simply is when one polar molecule, I'm not going to say one, let's just say this is when a polar is attracted to a polar. So this happens in polar molecules as well. This happens in all polar molecules where a polar molecule is attracted to another polar molecule. Water exerts some pretty strong dipole-dipole forces, but let me think of an example that does not include something that hydrogen bonds, like maybe HBr, the HBr molecule. Now in the HBr molecule, don't want to do Br, let me do Cl. In the HCl molecule, the Cl pulls electrons over, so on the Cl end we get a negative, and on this end we get a positive, and then if we take another and put another HCl in here, what happens? The H on that one wants to be near the negative on that one. See the opposite charges right here? The partial negative end and the partial positive end want to be near each other. Would it be likely for it to be this way, for an H to be attracted to an H? No, that's not going to happen. The positive end of the polar molecule is attracted to the negative end of the other molecule. Look right here in the middle. This is the key, right here in the middle. The positive end of one is attracted to the negative end of another, like a magnet, just like magnets. Now, why are they called dipoles? They're called dipoles because each polar molecule has two ends, a positive end and a negative end. And it's called dipole-dipole because one dipole can be attracted to another dipole. Cool, huh? These are second in strength. These are not as strong as hydrogen bonding, but still pretty strong. The last one is called London dispersion forces. This one can be pretty tricky. These are most significant in nonpolar molecules. Now, the reason I say this is important. Listen carefully. These are most significant in nonpolar molecules because the other two don't exist in nonpolar molecules. The hydrogen bonding and the dipole forces have to happen in polar molecules. Now, London dispersion forces happens in all molecules, but normally are not significant players in the polar and the dipole and the hydrogen bonding are not. The London dispersion forces are not big important players in the polar molecules. It's when the molecule is nonpolar that they really matter a lot. Let's look at this molecule. Fluorine actually doesn't like to be by itself. It likes to bond with another fluorine. And so we're going to put two F2 molecules near each other. And initially, these guys, because they're nonpolar, have electron clouds that are the exact same size. Do you see those exact same size electron clouds? Say yes. But because these electron clouds are made of electrons, which are moving around super, super fast near the speed of light, what would happen if at any one point, and this happens, this electron cloud got a little bit bigger? So the electrons temporarily shifted to the right. What would happen? Well, you don't have to tell me. Think it. This end would be a little bit negative, and then this end would be a little bit positive. Now, when this end becomes a little bit positive, what happens to these guys? Oh, they shift too. They shift in response. They say, oh, we'll do that too. If positive's here, what's going to be here? Negative is correct. So then this one shifts in response too. So that negative and positive can be near each other. Boy, that negative and positive stuff keeps coming back and keeps coming back. So what is the London dispersion force? It's a temporary shift in electron density that causes a temporary dipole. Okay, I want to finish this video by saying this about intermolecular forces, and this is a really big idea. Is it possible for the London dispersion force, which is relatively weak, is it possible for the London dispersion forces to be bigger than the dipole forces? It is possible. London dispersion forces really depend on the size of the molecule. Size of the molecule. A very large, write this down, I'm not going to write it. A very large molecule can have very intense London dispersion forces, making the attraction stronger than you might think. That's why oil is a liquid at room temperature. That's why wax is a solid. That's L and S at room temperature. Nonpolar molecules like to be gases, but these guys tend to be liquids and solids because they are extremely huge molecules. They are huge molecules, making the LDF, London dispersion forces, much larger, or very large, I'll say, extremely large. They are huge molecules, making the LDF, the London dispersion forces, very large. Okay, so when we say hydrogen bonding is the strongest, dipole-dipole is the second, and London dispersion force is the weakest, if they're the same if the molecules are relatively the same size, that's true. But if we get some really, really big molecules, the London dispersion forces can be much bigger than the other two. Isn't that neato? We'll be looking at demos of all of this in class. This is the end of part 2 on properties and structure.